Hello all, my name is Saif Hassan. I am software engineer at Facebook. Today in this talk I am going to present you about Open Routing Platform, short name for OpenR, specifically in the context of data center networks. Before we delve into the details of OpenR, let's take a look at how data center topologies are built and operated at Facebook. The current data center topology is built around clause topology. It offers many advantages over factory or other designs. First, it is built with commodity low radix switches. So you don't need a switch with like huge number of ports in the upper layer of your network. It offers flexible oversubscription ratio. So you can build your network as the demand grows. And it also has many equal cost paths between two end hosts in the network. We use this BGP for routing in the data center. The main reasons it scales very well with the growing number of devices and routes in the network, as well as it can leverage all the equal costs path effectively. However, there are some challenges with using BGP for routing as well as with clause topology design. The routing policies are getting very complex as they try to account for topology failure and route propagation loop prevention. On the top, the network is very over provisioned. We found that average link utilization is low in our fabric network, and it costs a lot to expand the network. For example, going from 4 planes to 8 planes, the number of devices and interconnects doubles in the network. The main reasons behind this is clause is designed to support the worst case utilization of the subnetwork, as well as it must maintain the symmetry for effectiveness of the ECMP. To address the inefficiency of clause, we are exploring alternate non-clause topologies such as BQ. They offer efficient networks with less devices and interconnects, but supporting the same number of end hosts. The discussion for non-closed topologies is outside the scope of this presentation. However, the non-closed topologies demands more complex routing solution. Take a look at this fully meshed topology on the right. From node 1 to node 3, there is a path over directly connected link, and there are two more paths through node 2 and node 4. However, the other two paths requires the non-shortest path routing capabilities. That means a data plane needs to support label-based forwarding, and control plane needs to support the source-based source routing capabilities. On the top, it has to be load aware because the network is shared. If the links connected with node 4 becomes overloaded, the path must be removed from the ECMP group on node 1. The richer data plane APIs in SAI can support as well as simplify the non-shortest path routing and load-aware routing in the control plane. The limitations of BGP and inefficiency of clause topology. At Facebook, we are working on OpenR. We designed and built from ground up. It's a distributed system that's responsible for routing in the closed networks. It is open sourced and runs on Facebook OCP designed switch stack, FPOS. It's battle tested with Facebook production network. As of now, it runs in the wide area network and data center networks and a wireless mesh networks. Now let's take a look deep into OpenR. At its core, OpenR offers the IGP routing protocol functionalities. So the question is, what makes up a routing protocol? Number one, a routing protocol needs to first discover who are its local peers. So that means a local neighbor discovery, very similar to LLDP neighbors. Once the neighbors are discovered, every node then needs to this information needs to be disseminated across the network so that all the nodes in the network knows about the neighbors of all other nodes in the network. That means they know about a global topology. On the top of this global topology, a simple algorithm such as SPF, shortest path first, can compute the routes from one node to another node. This distributed computation of routes on every node allows us to do loop-free routing. Then these computed routes can be programmed into the hardware. This picture describes the major modules in the OpenR. On the left, there is node 1 with all 4 modules present. On the right, there is node 2 with just 2 modules shown up. Between node 1 and node 2, it shows the inter-node communication patterns. Take a look at this picture. In the subsequent slides, we will look at each module at a time. Let's take a look at the link monitor. The link monitor module is responsible for discovering the local ports that are available on the system and monitor their status. On a link up, when a new port comes up, it starts discovering the neighbors on that link by UDP multicast messages. Once the neighbors are discovered, it tells KBstore to form a peering with the neighbors KBstore over the TCP sessions. It also inputs the local topology information into the KBstore. So link monitor, in short, monitors the link, all the links, search for the neighbors over those links, accumulate the neighbor information, manage the KBstore peering, and sets this local information in the KBstore. At its basics, it's a database that's replicated. The replica lives on every node in the network. It is very similar to NoSQL database, but much simpler. It supports setting string key values. The replicas on the nodes are connected with each other over the peer-to-peer links. And it provides eventual consistency. According to CAP theorem, out of consistency, availability, and partition, a database can only achieve 2 of them. And since the partitions is inherent to the network and availability is requirement for the local data access, read and write from the local node, we choose to go with eventual consistency. If you notice, there is no master. An update can occur on any node and anywhere. Further, the updates that are made to different nodes in the network can arrive on the 3rd node in the network out of order. It can arrive multiple times, or in a worst case, it can be lost. To address these challenges, KBstore implements a data structure called CRDT, conflict-free replicated data types. At the very basic, the idea for CRDT is we implement CRDT by having monotonically increasing values. We encode the value as monotonic version and data. Data is binary string. Every time data changes, the monotonic version increases, and we retain the higher value, means we retain the data associated with the higher version. This solves 2 of the problems we described. If the update occurs out of order, we just retain the higher version, lower version is ignored. If update occurs 2 times, it has no effect because we just retain the higher version. In terms of communication, when the KBstore first forms a peering with a neighboring KBstore, it performs a full sync to retrieve all the keys the neighbors they exchange with each other to synchronize. After this initial synchronization, any subsequent change on the node is flooded to all of its peered KBstore. A special logic has been added to detect the loops and prevent reflooding of the elements in the network. Further, to address an update that is lost in the network, we added anti-entropy sinks that randomly performs the synchronization with one of their neighbors periodically, that would restore like some of the lost updates in the very rare cases if they ever happen. This design greatly simplified the implementation of the KBstore distributed database and works perfectly well for all the practical use cases. The next, we'll look at the route computation and programming modules. The KBstore, as you can see, all the link monitor will submit their local topology. The KBstore synchronizes with each other. The KBstore will then have the topology information for all the nodes in the network. This information is fed into decision. After retrieving this information or an update about a topology from KBstore, the decision will compute the shortest path using an algorithm. This shortest path, the computed routes, are then forwarded to a fib module, which subsequently programs it into the hardware. The network is built up of many different vendor devices. Maintaining homogeneity in the network is pretty hard. In order to support OpenR on the different vendor devices, we abstracted out the hardware-dependent part with an RPC APIs. There are two main RPC APIs that a platform needs to support. One is to feed in the link state information, and next is to take the routes and program them in the hardware. In case of FBOSS, the FBOSS agent implements these APIs that helps us running OpenR on the FBOSS devices. This abstraction allowed us to run the same binary OpenR binary on different vendor devices. As we have seen so far, OpenR performs function of IGP. However, this modular design allows us to do much more than just the function of IGP routing. It allows various distributed applications to be built on the top of KBstore. If you look at it, the KBstore offers a data synchronization mechanisms across the node. We built few applications such as auto address allocation. When nodes joins the network, it allocates an address for itself outside from a bigger block. Our backup LSP path activation in our wide area network for a remote link failure. Further, it also can do performance-based routing. We added latency as the metrics. So OpenR can compute the metric as a part of handshake protocol with the neighbor when the neighbors are being discovered, and this metric can be fed in the topology for computing the routes based on the latencies. This is being used in the wide area network controller for computing the LSPs. Further, recently we added support for source routing capabilities as well as the non-shortest path routing. If you look at the decision consumes the topology information and compute the routes. Any different algorithm can be used for route computation. So far, by default, it implements SPF. We recently added a KSPF where it can compute the non-shortest paths and program the non-shortest paths using the MPLS labels by leveraging the source routing capabilities. It also offers a rich set of RPC APIs for remote network operations. For example, draining the devices or links. It also offers APIs to integrate the topology notifications. We use these APIs for managing the wide area networks remotely. All of this together is evolving at a speed to suit the needs of future network. In short, OpenR is a modern routing platform for modern networks. In order to use OpenR in the data center networks, we still had one challenge to solve: the interconnections at the border with BGP. Since BGP is the default routing protocol, an OpenR needs to interact with BGP to exchange the reachability information. To address this, we added a BGP speaker in OpenR that can send and receive the BGP encoded routes with the local BGP daemon. The redistributed routes, OpenR can understand the attributes and respect the BGP best path calculation, and it can as well transform this attribute backs when it hand over route to another BGP network. See, the OpenR is evolving at a very fast rate. That means every code change needs to be tested and checked in with confidence. Testing distributed systems, especially protocol, is very tricky. Further, using the physical resources, such as network devices, are expensive, and hence we cannot have many network devices to build large-scale testing topologies. In order to solve this, we use virtual topology that uses containers as the network nodes that are hosted on the physical server. A physical server can host up to several dozen, like up to 40 to 50 containers. This virtually meshed network can also emulate the real network conditions, such as latency for wide area network and loss for wireless networks. We test all the features in all different configurations on every code check-in. This really helps developers to make code changes much more confidently as well as frequently. Next, I would like to share some of the experiences of deploying and running this protocol in the data center network. This has not been an easy journey, and there has been many ups and downs in this. I would rather focus mostly on the very major learnings that we had. Number one is debugging distributed systems is pretty hard, especially the eventual consistency of KBstore. First of all, there are no stack traces as generally you can get in different programs because it's more or less event driven. And as we see, CRDT does not support deleting the keys. So we implemented a kind of the hacky solution to supports the delete. And it was pretty tricky to get it right. We experienced many issues such as inconsistencies in the databases across the node. To solve and tackle this kind of issues, we tried various solutions that effectively helped our teams to resolve them. First, we built a validator that can retrieve the state from distributed nodes and perform series of checks and tell whether things are inconsistent or is it leading to routing loops or so. Next, we built a Snoop that's a utility that can give the sequence of events that are happening in a system. With this, we can replay the same sequence of events in the emulation network and reproduce the failure. In few particular cases, we were able to replay the events such as bringing down link in certain order, and we could reproduce the routing loops and address them much more quickly than we could have done by analyzing the logs on the different devices. Next, it's a pretty interesting one. Usually we expect the network to have that, especially the data center switches, to have terabits of bandwidth, but there is a very limited bandwidth that's available for the control plane. Our initial implementation did not account for the limited CPU bandwidth that was available. That leads to a particular new release leads to choking of a CPU pipeline that leads to timeouts, and the neighbors were getting dropped. In order to address this, we added various optimizations in the control plane to reduce the exchange of data between the nodes, and as well as put the alerting about the resource consumption. So we monitor the CPU bandwidth and try to identify the regression with it in the initial phases of release before it gets widespread. There were issues around the backward compatibility as well. For example, a new release does not comply with the existing production release out there. This was very easy to address once we encounter a first instance of it. We run the emulation network with 50% of the current production network and 50% of the new binary that needs to go out in the production. This helps us capturing all the issues right there even before code lands in the repository. The OpenR is open sourced and is available on github.com/facebook/openr. There is a developer group that you can access and ask questions about the OpenR. We encourage you to use, improve, and contribute on the GitHub. With this, I would like to conclude my talk and would be happy to answer the questions. Thank you.
Hello. I'm answering one question from the chat. I have tried to answer. I'm Saif here. I have tried to answer a couple of questions through the chat. One of the interesting questions that Jack put up is, if you use latency as metrics, how often would you update metrics if it fluctuates? So the OpenR in the neighbor discovery process, it implements the RPT measurements, and it is measured on the ongoing basis. And if it fluctuates, we kind of put something like step detectors, which can be configurable. For example, if it fluctuates by 5%, then use the new RTT. So there is a dampening as well as a step detection, which can help reducing the too many updates if RTT fluctuates. In the stable networks, it doesn't fluctuate, like mostly the wired networks, but it can fluctuate if, for example, a fiber cut happens and circuit is routed to another fiber. So RTT may jump from 25 milliseconds to 30 milliseconds. Another question is from Benjamin: is anyone else using or deploying OpenR outside of Facebook? There have been some of, I'm not sure exactly who uses it, but we have been have a working group in Facebook, which is public group. There have been few people who have been trying to use OpenR in the context of their wireless network. Apart from this, Facebook has a Terragraph network, which many of the providers uses it, and OpenR is the native routing protocol in there. There is another question from Tao. What is the motivation to create another link state routing protocol instead of extending the well-known OSPF or ISIS to support desired performance-based routing? We kind of revisited this in the initial stage when we started working on OpenR. There were some of the few things is we started working on OpenR in the wireless context, and we had certain set of requirements which was kind of hard to get from OSPF and ISIS. Number one, there was no good open source implementation that was available with of OSPF back then and ISIS to make it work with the devices we had. Two was we needed to do certain things like remote operations on the devices. So one of the requirements for wireless network was to auto bootstrap the network. So as more and more nodes joins in, they would auto configure themselves and will then enable their peers to configure. So this was something kind of was hard to achieve, especially the integration with the remote controller. And Because of this, like we thought of like starting with like a prototyping, and it turned out to be pretty good, and we kind of started adopting into different like data center networking scope as well. The next question, is the protocol spec open source? The protocol itself is open source. I would not call it kind of as a protocol because we don't have like the RFC style guides that BGP, OSPF, or ISS protocols would have. Rather, it would be more about like a software system that's out there. The documentation associated with in the GitHub would explain like the design, the integration, the RPC APIs, and how to configure it. There is a question, what would you say is the major advantages over iBGP from Jack? That's a pretty good question. I would not kind of rate BGP and OpenR, say which one is better. Both has their own advantages as well as kind of disadvantages. For example, OpenR can only work, or it's an IGP, can only work in the closed networks. At the border, it needs to interact with other protocols. The main few advantages that we could kind of see in our own network was to specifically like support the topology aware routing. With this, like I mentioned before, is supporting especially non-closed topologies and load aware routing, which would be kind of hard to extend and achieve in the BGP. Like if you can think of like non-closed topologies would require the paths like a shortest path and non-shortest path both to be programmed. However, BGP can mostly work with only the shortest path. One specific example I can kind of give is we easily kind of extended and implemented the source routing capabilities in OpenR, with which we can achieve non-shortest path routing, but with BGP it can do only IP routes. There is a question from Amrinder. How is the compatibility of OpenR to run along with other IGP protocols? So as of now, OpenR does not work with any other protocol except the BGP that we kind of covered in one of the slides, where OpenR has a BGP speaker and you can configure it to receive and send route with one BGP daemon, which would be the local BGP daemon. The neighbor discovery like part, or the KBstore communication part, so it's kind of a closed protocol, so it doesn't kind of work well with any other protocol. Except at the area border, you can like kind of import the routes and feed the routes to other protocols. I will wait 30 more seconds for one more question. There is a question from Abhiram. Do you have some statistics about performance of OpenR? So there are like the performance would kind of depend on the nature of the network, the latency of the link, and so on. But if we kind of characterize performance as the convergence time, in our data center networks, when we measure the performance, it's in like order of 50 to 100 milliseconds when it converges for certain link events. But it can be configured to be even more faster. But then, like if the decisions are run very fast, more CPU will be churned. So there is usually IGP implements some kind of backup mechanism to accumulate the updates and run the like run the path computations in the interval of like 50 milliseconds or so. There is a question from Jeff. Have you extended OpenR to exchange label binding? As of now, no. It supports mostly the auto label generation, and it implements the source routing RFC, but in its own kind of way, where in unique node label adjacency labels and programs those label routes in the MPLS field. There is a question from Abhiram Kaluru. How many data centers are running OpenR already? We are kind of now starting to use OpenR in our data centers, and we are kind of experimenting with it. So it's not like widely used, but we have started to use in the data centers. I can't exactly answer how many for confidential reasons. Question from Ravindranath. Does it support warm boot? So if like I'm considering warm boot as the Graceful Rustad. So yes, very similar to BGP, OpenR also supports the Graceful Rustad capabilities, where you can restart a node, wait for like 30 to 60 seconds, depending on the time you configure, the GR timer you configure for upgrading the process or configuration update, and restart the process afterwards. So it does support the warm boot in that sense. If you use ECMP with iBGP, you will be using all paths, not just shortest. I could not get the question. This one, Sandeep. Question from Jeff. How does it implement UCMP? As of now, OpenR does not implement UCMP, but that is something internally we have been working to extend it. It would work just like from top of my head, it should work very similar to what BGP, like the link bandwidth communities, and with some more capabilities on the top. But as of now, it does not. This question from Satish, where can I find OpenR project details? You can go to github.com/Facebook/OpenR. That's where all the project and all the information, including code, is there. All right, I would kind of, maybe I see no more questions, so we can conclude here. Thank you all for joining today, and we will end the presentation now. If you have more questions, you can reach out to the OpenR Facebook group to know more about this. Oh, wait, there is one more question. The question from Ravindranath: with eventual consistency model, transient routing loops are possible. How do we handle them? Yes, it's the convergence of the KBstore is like the convergence of the database is important in order to not have routing loops. Um, the way we kind of handle them is to rely on the eventual consistency to happen, and then the eventual time would be the convergence time. So faster the KBstore converges, the faster would be the reaction time to the network changes. The KBstore slides, those are there, that should cover in like how do we recover from a lost update, or how do we convey the information update, whether it's a route announcement or a topology change in the network. That's through the flooding and synchronization. All right. We can then conclude our presentation now. Thanks all for joining today.